Let's learn two very important formulas that will be useful in calculus, differential equations, and other courses. So, what are those two formulas? So, the first one is integral of 1 over x squared plus a squared dx, and we know that which is equals to 1 over a tan inverse x over a. Some people write tan inverse as arctan, so arctan x over a. Okay, it's the same thing. Okay, now let's see how we can prove this one. So to prove this one, so this is a what we normally call a trig sub problem. So we can use a familiar trig substitution here, which is x equal a tan theta. So if you say x equal a tan theta, and you can see that the theta is in between negative pi over 2 to pi over 2. The reason is, and you can see in that on that domain, tan goes to from negative infinity to positive infinity. So that means it's going to cover the full range of the x values. So there are no restrictions. That's one of the very important feature about this one. And then let's see what happened to the substitution. So when you use a substitution, first thing you can take the derivative. So once you take the derivative, you can see that you get dx equal a. Derivative of tan is secant squared. So you get dx equal a secant squared d theta. And then what we also need to know what will happen to the term in the denominator x squared plus a squared. So we're going to use a substitution. So when you do the substitution, this is what happens. So you can see x equal a tan theta, and then we have a squared, and when you pull a squared out, you can see you get tan squared plus 1. Tan squared plus 1 is secant squared, that we know from trigonometry. So that means x squared plus a squared equal a squared secant squared theta. With this substitution, this integral is going to be really easy. You can see what will happen when you substitute. So when you substitute, we have 1 over x squared plus a squared dx. So the first term, x squared plus a squared, is going to be a squared secant squared theta, as we just proved. And the derivative dx part, we also know what is that. So when you substitute for that, this is what you get. And then you can see it simplified really well. So secant squared theta get cancelled out. You can pull 1 over a out. So when you pull 1 over a out, you get d theta. That's the only thing left. D theta means when you integrate, you get theta. So 1 over a theta plus c. So that's the answer. But you can leave it like that because you need to replace theta by the substitution or some other functions. But for that, we can go back to the substitution. So the substitution is x equal a tan theta. When you divide by a, you get x over a equal tan theta. And when you invert it, you get theta equal tan inverse x over a. You can easily invert this one because of full range. So you get theta equal tan inverse x over a, and then you can substitute that back into the formula, and then you finally get 1 over a tan inverse x over a plus c. So this is how you prove the first formula, and this is very important formula. And then also now let's look at the second one. The second formula is integral of 1 over x squared minus a squared dx, and here you have a negative sign. So you see that, so it's not the same answer as you get last time. You get a completely different one. So what you really get is this one. You get 1 over 2a, that's a 2 here, ln absolute value x minus a divided by x plus a. So how to prove this one? So we normally prove something like this one using partial fraction method. Um, So let's see how the steps are going to work. So we're going to start with the integral. We have 1 over x squared minus a squared, and you can see that you're going to factor that as x minus a x plus a. Because of that, you can write the partial fractions. You get two partial fractions. So it's the first one and the second one. It doesn't matter which one. We normally write the smaller one first, just to get positive answers, positive a. And so that's like kind of trick we do. And then we normally use a normal procedure for this one. We can use a substitution technique. When you substitute, so actually after that, what we normally do is we're going to multiply by this term both sides. That's what we do. So when you multiply by this both sides, you get the first one is going to be 1 identical to a x plus a. You get the other one. So switch. And then similarly, for the next one, again, this can go there. Okay, so it's clear how the algebra works. And then we use substitution technique to find it. So we're going to substitute x equal a, that one, that's 0. Then you get x equal a, yeah. So and then you get a in this case. So a equal 1 over 2a. Similarly, you substitute x equal negative a, then this term get cancelled out, and you get b equal negative 1 over 2a. So we know both, and then we can substitute them. So when you substitute, you get 1 over x squared minus a squared dx, and then you can see you can pull the constant out, both constants. So you get 1 over x minus a and 1 over x plus a, and we know what is the integral of that. So 1 over x minus a means natural log x minus a. 1 over x plus a means natural log x plus a, and then we can combine them into 2 because you can see it's the same factor, 1 over 2a. So we pull it out, and it's a log difference. Log difference means a division. So you can write it like this now. So the final answer is 1 over 2a ln x minus a x plus a. Okay, so this is the second important formula. So now let's put all of them together. So and also there is a argument, because sometimes we don't see this way, we sometimes see a squared first. So if you see that one, you can actually switch them, because when you switch, it's a negative sign. Negative sign means in the log what will happen, you're gonna flip over. So these two terms flip over when you put a negative sign here. So that means we can also get this one. So if you flip them, if you flip the terms, you're gonna flip these terms. That's the idea. So, and you can see x minus a now is in the bottom. Earlier it was in the top, now it's in the bottom. So remember this argument is when you flip, you're gonna flip the fraction. And also, if you need the same format, because here you see a first, you can actually do that. You can just write it like this one without any problems. The reason is it is under the absolute value sign, so it doesn't matter even if you flip, you just give a negative sign, yes, but it is under absolute value sign, so it doesn't make any change. So that means that's what you get. So and this way it's easy to remember. See the same pattern, a minus x, so a minus x, so like that. So you can remember like that if you want. Because when you get the plus sign, um, we get the tan inverse, but when you get minus sign, you get this one, and then you see minus is in the denominator, so you can remember it like that, so if you want. So those are the two most important formulas that we use in calculus and differential equations and other classes. So let's put everything together, and these are all the formulas that we learn. The two major formulas and the alternative version of that. So now let's try to look at few examples and see how we can use this idea in problems to save time, because you can save a lot of time just knowing this one. So let's look at the first few problems. So let's say evaluate 1 over 1 plus x squared plus a squared. So in this case, and you can see, you can write this integral as 1 over, which is x squared, and 4 you can write as 2 squared, because we need to figure out what is a. So a in this case is 2. Since a is 2, you can write this one as 1 over 2 according to the formula tan inverse x over 2. So that is the answer for the first one. And you can see you can get the answer really quickly. So let's look at the next one. So instead of plus, now we have minus. So that means the other formula. So that means we can write this one as, in this case, again, same argument. So we can say 1 over x squared minus 2 squared. So that means according to the formula, so it is going to be 1 over 2a. So in this case, a equal 2. So a equal 2 in both cases. So because a equal 2, so you get 1 over 4 natural log, and then x minus 2 over x plus 2, absolutely, plus c. So that's the answer for the second one. And let's look at the third one. So as the next one, we have 1 over x squared plus 3. One of the difficulty here is you don't see this square here. Like in the formula there should be a squared, but what we can do, we can rewrite this one. So we can rewrite this one as x squared plus, you can say it is square root 3 squared. So that is the idea, square root 3 squared dx. Now we know what is a. So now a equal square root 3. So we can plug in that in the formula. So when you do that, you get 1 over square root 3 tan inverse, and you get x over square root 3. If you want, you can rationalize the denominators, but that's not a big deal here. Okay, so let's look at the next one. As the next one, we have a little complicated one. We have 1 over x squared plus 2x plus 3. One of the difficulty, you don't see any squares here. So that means we can use the completing square argument for that. So it is 1 over bottom. You can see that you can write this one as x squared plus 2x, and we're going to put one of them with this one, because you can write the this one as x plus 1 squared and leave the rest. So that's the idea. And when you do that, and you can see this is simply 1 over x plus 2, not x plus 2, x plus 1, x plus 1 squared plus 2, you can write as square root 2 squared. So that's the idea. And then you can integrate this one easily now. So it is again 1 over square root 2 tan inverse. Now what happened? It's not x, it is x plus 1. So when you have constants, you can just treat this one as exact like x. Formula does not change. So that's because the substitution, you can use the substitution u equal x plus 1. And when you take the derivative, dx equal du equal dx. Because of that, this works exactly the same way. So that means this is simply tan inverse x plus 1 divided by square root 2 plus c. Okay, so that's how we do it. So let's do one more example with just a little bit, hard problem. So this is the last one. That's the last problem. We have this one, 1 over 3 squared minus 12x plus 11. So see whether you can actually integrate this one using any of those formulas first. So you can stop the video and you can try it. So the question is how to do it. So what we can do, as in the previous example, we use the completing square. So we can pull 3 out from the denominator first. So we can write it like this. So we have 1 over, if you pull 3 out, so you're gonna write this one as x squared minus 4x. That's what we get. I'm gonna leave some space and we have plus 11. Now to write this as a complete square, you know that you need the half of that, which is negative 2 and squared. So that is a special term that we need. That means which is 4. So you add a 4, but when you add a 4, you're actually adding 4 times 3, so 12. So just to match that, we subtract 12 from this one. That's how you do the algebra here. Now you can see you can write it like this because of the completing square part. Now what we do, we pull 3 out. 3 means 1/3 out. Then you divide 1 by 3. So the second term, actually you can write 1 over square root 3 squared. We can write it like that. And in this case, you can see that a equal 1 over square root 3. Now we can use the second formula to write the answer in this way. You can simplify this to get this one. This is how you can use those two important formulas to get the answer to certain type of integrals that you can write as 1 over x squared plus a squared, or 1 over x squared minus a squared. Okay, you can try these as practice problems now. Try these as practice problems, and also you can try these two as little challenging ones. And if you know how to do them, you can put the answers in the comment section. So please remember this one. This is like a really nice trick, and that can help you to solve many problems very quickly. Thank you so much for watching.